In this lecture, I am going to explain you Ligancy 4. That is, we are going to find critical radius ratio for Ligancy 4 in this case. The diagram, as you can see, in the first plane, there are three anions which are touching each other. Say this is 1, 2, and 3. All three anions are in contact with each other, and at center there is a cavity. All three anions are in the same plane, and at center there is a cavity, or you can say it is a tetrahedral void which is occupied by cation, and then this fourth anion sits on this, and you get the structure shown like this. In this case, you can see these three anions 1, 2, 3, and one is backside. All four anions are in contact with each other, so they are forming a tetrahedral structure. And the cavity at the center, or the void at the center, is called tetrahedral void, or in this case it is called the centroid. Centroid position is occupied by cation. Now to find critical radius ratio for ligancy, what we will do is we will join the center of all the four anions with each other this way, and one is a backside, and then this, then this. So we are going to draw a tetrahedron, and here is the diagram of the tetrahedron. In this case, at point A, D, C, and B, at these points there is anion. At each point there is anion, and these anions are in contact with each other along the edge. For example, you can take length AB. This length AB, along this length, anions are in contact. Similarly, along the length BC, anions are in contact. Similarly, along the length AC, these anions are in contact, as well as they are in contact along length AB, along length AB, and along length AC. So all these lengths are equal because along that length anions are in contact with each other, and that is equals to twice the radius of anion. Because here, as you see, they are in contact with each other. So this length from here to here is twice the radius of anion. And you know that in this diagram, that if you consider triangle ABC, or this triangle, this ABC, this triangle is equilateral triangle. Similarly, if you consider triangle BDC, that is also equilateral triangle. Similarly, triangle ADB, this is equilateral triangle, and one is backside. So there are four equilateral triangles are forming in this case. Initially, we will consider equilateral triangle ABC, and we will draw medians to this equilateral triangle. Let me show that diagram to you. Okay, here. As you can see in this diagram, triangle ABC We will consider only first triangle A, B, and C. Is equilateral triangle. Equilateral triangle. And then we will draw medians to this equilateral triangle, which are already drawn and shown. As you can see in this case, this AE is one median, then this CG is another median, and then this BF. All these three are medians. Okay, the medians are AE, BF, and CG. Okay, medians of equilateral triangle. And you know the rule that these medians of equilateral triangle in, intersect at point T. Intersect at point T in the ratio 2:1. Okay, this T point T is the intersection point, and at that intersection, these medians intersect in the ratio 2:1. Means AT is twice 2 part and TE is 1 part. To find out exactly how much is the median length, we will consider here the right angle triangle AEB. Here consider triangle AEB. This is the triangle we are considering. AE and B. In AEB, as you see in the diagram, angle E is 90 degree, length BE is RA, and length AB is equals to twice RA, because AE is half. This BE is half of BC. BE is half of BC, so that is equals to RA. So from this triangle we can find, what we have to find is length AE. So find out that length AE is equals to square root of length AB minus length BE, and which is equals to AB is twice RA, so this is 4 RA square minus BE is RA, so minus RA square, or that is equals to root 3 RA, which is equals to length A. Now at point T, the medians intersect in the ratio 2:1. It means that length AT is equals to 2/3 of length AE, that is 2/3 of root 3 RA. is length AT. Similarly, length TE is equals to 1/3 of length AE, which is equals to 1/3 of root 3 RA. So we got these two lengths, length AT and length TE. Then we will consider here another triangle to find the height of the tetrahedron. Okay, let us find the height of the tetrahedron. I have inserted the diagram again. So now in this case, now I will consider the triangle ATD. Okay, I am considering this triangle. This is AT, this is DT, and this one is side AD. So I am considering this triangle ATD. In this triangle, as you see here, angle T is 90 degrees. Length AT, we know the length AT. Just now we found the length AT. This is length AT. Two third of root 3 RA. That is length AT. And we know the length AD, along which two anions are in contact with each other. So that is equals to twice RA. Then what we have to find is DT. Length DT. Length DT, which is nothing but height of tetrahedron. So length dt, using the Pythagoras principle, length dt is equals to square root of length AD square minus length AT square. Substitute the values of length AD. AD is nothing but 2RA, so square of that is 4RA square, and AT is this, and square of that is 4 by 9 into 3RA square. And if you simplify it further, you get length dt is equals to 2 root 6 upon 3RA. So height of the tetrahedron we calculated, which is equals to 2 root 6 by 3RA. Okay. So I don't want to move it up and down, so I will insert the same diagram here. As you can see in this case now, we will consider another equilateral triangle, which is DBC. Consider triangle DBC. So you can see this triangle. This is point D, this is B, and this is C. So we are considering this equilateral triangle DBC, and which is equilateral. And medians to this triangle are you can see DE. Okay, from D to E is one of the median. Then let's say this point is N and this point is M. Then another median is CN, and the third median is BN. These are the medians of that triangle. And these medians intersect, okay, these medians intersect at O, at point O. So you can see then the diagram, it's AO. What is AO? In this diagram, this A and this point O. This AO is also height of tetrahedron. It means AO is equals to dt, and we already know the height of tetrahedron is nothing but 2 root 6 by 3 Ra. We have calculated dt over here, 2 root 6 by 3 Ra. Then let us find out how much is DO. We will find only how much is DO. This DO is, we know that DE is equals to length DE is equals to length AE, length of median, and which is equals to the 2/3 of, which is equals to, sorry, root 3 Ra. And this DO is 2/3 of length DE. And so DO is equals to length DO 2/3 of length DE or length AE, that means into root 3 Ra. So that is the length DO. Let me insert the same diagram once again. I don't have to move up and down. So here. Now we will consider two triangles here. Consider triangle DTE. DTE. That is, this is the point D, this is the point T, and this is the point E. DTE. And DOX. Consider triangles DTE and DOX. This is the point O, intersection point, and this is the another point. So if you look at this two triangle DTE, this DTE and DOX, in these two triangles, angle D is common to both, and as you can see here, this is angle 90 degree and this is angle 90 degree. So one angle is common, okay, one angle which is D is common, and other angle is 90 degree. So two angles are the same, and so these two triangles DTE and DOX are called similar triangles. And when you say they are similar triangles, then we can write XO, this length XO divided by TE, this length over here, and that is equals to DO, That is the length from this point to this point, which is DO, and that is divided by dt from this point to this point. Okay, for similar triangles, we can write such equations. xo by te equals to do by dt. But when you look at this diagram carefully, then you can see that by symmetry, this xo, this to this, is equals to xt. xo equals to xt. At point x, two heights are intersecting, and that is the point where there is a center of cation. At point x, there is a center of cation. That is the centroid. And so this xo is equals to xt. Then we can write this equation as, modify this equation by, we will replace xo with xt, and so xt by te is equals to do by dt, or this xt, what we have to find is xt, the distance between this point to this point. We already know the distance dt. In this diagram, we already know how much is distance from point D to point T. Now we have to find this distance between x and t. If we know xt, we already know dt, then we can find dx. And along the dx, cation and anion are in contact. That's why we have to find dx. So xt is equals to te into do by dt. We know all these right hand sides. te, we know that te is 1/3 of root 3 Ra. This is nothing but 1/3 of root 3 Ra into do. This is do from here to here, and that distance is 2/3 of root 3 Ra divided by dt, which is the height of the tetrahedron, and that is equals to 2 root 6 upon 3 Ra. Now you can see in this equation, this 2 by 3 cancels with this 2 by 3. This root 3 into root 3 cancels with this 3. This Ra cancels with this Ra. And so what is remained is Ra upon root 6. So this xt is equals to Ra upon root 6. Now as in the diagram, you know dt from here to here, which is the height of the tetrahedron, that dt is nothing but dx plus xt. That dt is dx, x is here, and plus xt. And what we have to find here is dx. Dx is dt minus xt. Dt is the height of the tetrahedron, and that height is 2 root 6 upon 3 Ra minus xt, xt is this, Ra upon root 6. And that is equals to dx. Now along the dx, cation and anion are in contact. So dx is nothing but Ra plus Rc, and that is equals to this. If you take 2 Ra common, not only Ra common, and in bracket it is 2 root 6 by 3 minus 1 by root 6, or Rc. Let us find Rc. Rc equals to Ra 2 root 6 by 3 minus 1 by root 6 minus 1, and that is nothing but 0.225 Ra. After simplification, you get 0.225 Ra, and hence Rc by Ra is equals to 0.225. And this is the critical radius ratio for Ligancy 4. It means that Ligancy 4 is possible when Rc by Ra is in between 0.225 to 0.414. 414 is critical radius ratio for Ligancy 6. Ligancy 5 is not possible.